Hi everyone, welcome to video number 1 in a series of videos that's going to show you how to troubleshoot electronics, solid state and vacuum tube without the need for schematics. Now, for those of you that are uncomfortable starting off like this, I will include a schematic underneath this video if you want to follow along doing that. And there'll also be another attachment there. It's actually a picture of this board with a bunch of numbers on it, and I'll explain that here as we start with the video. So I've mentioned this in some earlier videos that we're going to follow the signal path through the amplifier chain all the way up to the display IC, and that's what we're going to do in this video, and I'm going to show you how that signal gets amplified and where to probe in a circuit so that you can actually find an issue if it exists. Now, this can be used for any type of an amplifier circuit, whether it's vacuum tube or solid state. You basically just need to know where to put the probes. There's a lot of things out there that will aid you in your troubleshooting procedure that has nothing to do with the schematic. A lot of the time, just knowing the pinout and what type of transistor you have on your circuit board is enough to get you going. Same thing with a vacuum tube. If you know what type of vacuum tubes are plugged into the circuit, you can very easily find out where the cathode grid and plate are, and you're on your way looking for a signal that may have gone missing in some stage. So what I'm going to do now is I'm going to get a bunch of test gear hooked up to this thing. I'm going to explain how I've hooked things up. I'm going to use an oscilloscope, and I'll show you how things get amplified through all of the stages and what happens with all of these components to make this little circuit board do what it does. So let's get started. In order to start troubleshooting or following the signal path in our SIFT amplifier and display board, we can use some common knowledge just to figure out how we need to hook this thing up in order to start following that signal path. So we can use the experience that we've gained in the last couple of videos without having to have a schematic ahead of us here to figure out a few very simple things. For example, I'll use another piece of gear, for example. So say you had a home stereo system sitting on the bench in front of you and you needed to troubleshoot that audio amplifier stage in your home stereo system. Well, obviously, in order to troubleshoot an amplifier, what are you going to need? Some form of signal, right? So in order to troubleshoot an amplifier stage in this SIFT amplifier, or just to follow the signal path, what are we going to need? We're going to need some form of a signal at the input to feed to the input so we can follow that signal through the different stages right up into the display. Now, from the previous videos about this SIFT unit, you also know that by us just touching a capacitor is enough to bring this display right to its maximum. Now, since we know that, we would obviously know that if we're touching a capacitor that basically has one end grounded and the other end running into the input here, if it can move this bar graph right to the top of the display, what is that telling us about this amplifier? This amplifier is crazy sensitive, okay? Now, I will tell you this. This amplifier is so incredibly sensitive that it's running within the sensitivity of a standard radio receiver. For example, in order to take this light display and bring it right to the top here, it takes under 50 microvolts to make this come right to the top. Many radios that I've aligned in the past have specs to align it for 85 microvolts for S9. So that's 85 microvolts of signal fed into the input jack to give an S9 signal, which is almost a full display on some of the smaller radios. Now, of course, you have 10 and 30 dB over and things like that, but you know, the scale's way up there. Now, this takes 50 microvolts or lower in some cases to bring this display right to the top. That already tells us that this thing has the sensitivity of a radio receiver. If I was to attach this to an antenna, this display would just go right to the top and it would listen to just random noise and hum, right? So, in order to look at a signal that is going to be about, we'll say 50 microvolts right now. We'll read it and get an exact signal here in a bit. In order to look at a signal that is 50 microvolts or so, standard oscilloscopes will not see that. You need a very expensive amplifier box that sits in front of your oscilloscope that's basically a very sensitive preamp to take a signal that low and amplify it so that you can get proper readings off your oscilloscope. Now, those boxes are thousands of dollars to make your oscilloscope do that. Well, we don't need to do that because we're going to design our own that's going to do that for a fraction of the cost, under $100, easy. So at any rate, we're going to do that here in the future, and we're going to make it take, say, a 10 microvolt signal and amplify it to maybe 100 millivolts. So we'll make it even. So we can do the math to figure out exactly what our input signal is to the output signal. And we're going to do that here in the near future. So it'll be a very, very sensitive amplifier project, and that will teach you a lot about keeping circuits quiet and noise figures and things like that. We're going to dive right into that kind of stuff as well. So another really neat piece of equipment is going to be coming here in the near future. Now here's the thing, in order for me to look at this signal, I have to use a very expensive piece of gear, which is called a spectrum analyzer. My spectrum analyzer goes very low in frequency, so what I'm going to do is I'm going to attach my spectrum analyzer to the input here, and I'll show you the actual level that in microvolts that's going into this thing to make this bar graph go right to the top. Now, my oscilloscope, if I use the zoom feature, I can see the signal at the input with some pretty extreme zoom, but it's a very dirty signal and all the math and everything displayed on the screen is pretty much gibberish. I can just see on the oscilloscope screen that there is some form of amplitude there. Now, in a case like this, if you're going to ever troubleshoot anything that's this sensitive, and I can pretty much guarantee you that unless you're working with a device like this, you're never going to come across anything that's going to be this sensitive in the audio game at all. This is a pretty specifically designed device. But if you are ever looking for a low-level signal like this, what you usually do in a case like this is go through the first amplifier stage on the device itself and look for the signal at that stage. If you can see an amplified signal over here, it gives you an idea that the first stage is working. That's a way you can kind of cheat if you don't have the test gear, and I've done it many times with older oscilloscopes. It works just fine. But it is nice to have that actual readout so you can trace those, basically sub-microvolt kind of signals, right? So a lot of really neat stuff coming here. At any rate, what I'm going to do now is I'm going to turn my signal generator up. I'll give you an idea. So I'll just get my hand close to the jack on the signal generator. Look at this. That's how sensitive this thing is. Again, this thing has the sensitivity of a radio receiver, right? So what I'm going to do is reach way over the jack and grab my amplitude control and turn this up. Just going to crack the sensitivity control open, and as you can see we get a full display. Now my signal generator, it's very hard to do this because I'm introducing a little bit of noise myself. There we go. So yeah, you can see I moved my hand away. There we go. So I could probably use just a little bit more amplitude. You know what that probably is? This is a Wien bridge oscillator inside the audio generator that I'm using, and there's probably temperature variation going on in it. That's how incredibly sensitive this thing is right now, right? Because the amplitude is so incredibly low. If I give it just a touch more amplitude, I'll probably be able to keep that last LED on. There we go. So the signal generator is down to nothing. This is just sniffing a signal coming out of this thing. So you can use any type of an audio signal generator to test this thing. If you find that your audio signal generator doesn't go that low, it's extremely simple to make an attenuator to basically take that signal right down to nothing. And we'll design some of those here in the future as well. Maybe we'll design some for the ICO signal generator and things like that. An attenuator that'll basically cut all the signal right off, way, 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 way down. Right down into the extremely low microvolts, maybe even into the nanovolts. So we'll do that as well in the future here, just to make, whatever piece of test gear you have, whether it's vacuum tube or solid state, versatile to use in an application like this. So what I'm going to do is I'll hook up my spectrum analyzer now to the inputs here, to the input here. So basically, it's going to read the signal coming out of my signal generator right at this point here. We'll take a look at the level of signal that it takes to make this bar graph go right to the top here. And once we've established that, we can write that figure down, and I'm going to show you how to do the math to figure out the gain of an amplifier section like this as well in this video. I have the input of the spectrum analyzer attached to the output of my signal generator right at the SIFT board itself. So where you saw that BNC jack earlier with the alligator clips, I've just clipped the input of my spectrum analyzer to that point. Now, since there is a little bit of exposed lead length there, the spectrum analyzer is set to such a sensitive setting that it's going to see some 60 cycle noise. So what I've done is I've moved the signal generator just a little bit above 60 cycles so that we can get a nice clear picture of exactly how much amplitude it takes to light up all the LEDs on the display of that SIFT amplifier and display board. So I very carefully adjusted the amplitude already just until the last LED fully lit. So right now it's fully lit and I'm ready to do a single pass with the spectrum analyzer. So let's take a look at exactly how much amplitude it takes to light all those LEDs up. Here we go. So we'll do a single pass. So you're going to see a bump right in the center of the screen. That's at 60 cycles, and actually there's some noise off to one side of it. You can see it's not right in the center. The second bump that you see right now forming is the signal generator's output. So what I'm going to do now is I'm going to move the marker right to the maximum amplitude there, and we'll see exactly how much it takes to drive that board right up to the last LED. Right about there is at the peak. So as you can see, it's taking 27.5 microvolts to drive that display right to the last LED. This really does have the sensitivity of a receiver. So you're going to want to mark that down on a piece of paper, 27.5 microvolts. If you want to convert that into volts, that's 0.0000275 volts. Just before we get started following the signal path through the SIFT amplifier and display board, below this video are a couple of attachments that you should download and print off. One of those attachments being this picture right here with numbers on it showing the different test points as we go along through the amplifier section and up to the display IC right here. The second attachment that you should download is the schematic. Now, for those of you that don't feel comfortable troubleshooting this without a schematic, there will be a schematic underneath this as well. So this is the most current schematic. This is for the completed device that you've seen in the last video. This has the switching in the bottom portion here. So the board that we're testing starts right here, and this point right here really is this point right here. So if you were to draw a cut right here and feed the signal in at this point right here, right where that little dot is by the 4.7, the signal will go up into here, and this up here is the same as what you see right here. So it's just basically cutting off this bottom section here. So when we looked at the spectrum analyzer, the signal was fed right into this point here with this line broken right here. So you can ignore all of this, and the signal just went in here, and this is what we're doing. So we're actually measuring the signal at this point, and that's where we're going to be starting off here. Now, I will make reference back to the schematic every now and then if I need to explain something, in a little bit clearer detail, I guess you could say, in order to maybe explain the signal process here. But for those of you that don't want to follow the schematic, I'll try to keep the schematic out of this as much as possible so that we can just focus on looking at the circuit board and figuring out how we should be troubleshooting or following the signal path through this. Troubleshooting and following the signal path really fall along the same line. So that's what we're going to be doing next. In order to start off this troubleshooting procedure, the first thing that we want to do is take all the knowledge that we know about circuits like this, things that we're familiar with from working on other things, and put that to use here. So first of all, some of the things that we already know about this circuit is that we have an input here, and that would be pretty obvious if this was an audio amplifier because it would be running up to some form of an audio jack, whether it's an RCA or BNC or XLR or something like that, right? Now, the rest of this would be simply following the traces. So we can see that we have a trace here, we have a resistor that runs to ground. You can see that we have a trace that goes up through a ceramic capacitor and runs down to here and into this area here on the transistor. Let's grab something to point with here. into this area right here on the transistor, this little pin right here, or leg if you like. So we know that the signal would be going through this capacitor and over to here. Now, if we didn't know what kind of a transistor this was, is it a FET? Is it a PNP transistor? Is it an NPN transistor? If we don't know what's going on here, we can very simply find out what this is, because the pinout for these transistors is very, very standard. So what we could do is just take a common data sheet. I have the data sheet for this particular transistor right here, and you can find these online, or if you want to save a piece of paper, you can just draw this down right now. So this is that transistor right here, SOT23, and as you can see, it very comfortably labels base, emitter, and collector. Now this is the same for PNP transistors as well, and we wouldn't know at this point, if we're very quickly looking at this, what we've got going on here. So one way to very easily verify this is just to use a standard diode checker on your DMM. So you can see why I used this in this application. Right? This device is designed for low noise, high gain, general purpose amplifier applications. It's the reason that I chose this 5089, because it is a pretty high gain transistor. So if you want to write this down, just draw a rectangle on a piece of paper and draw a couple little squares for the legs and just label them base, emitter, and collector. You might find that helpful in this troubleshooting process. So now, if you want to very quickly verify what you have here and how it's hooked up, because at this point we wouldn't know if this was an unknown design, we wouldn't know if that was, as I say, a FET or a PNP, NPN, whatever they've put in here, right? So you want to grab a DMM. I have a video on YouTube that shows how to do the check here with just a standard diode checker. So what I'll do is I'll just back this out until I can get my multimeter in here. There's quite a bit of glare on this. If I can put something under here. It's hard to get both devices in focus at the same time, so I'll switch back and forth. So we know already the pinout because it's very standard. So we know that this is the base, this is the collector, and this is the emitter right here on this little transistor. So if we wanted to check for an NPN transistor, right? N being the collector, P being the base, and N being the emitter. Now you can select or move around the emitter and collector in this test. What I'll do is I'll also post that video on how to use a standard diode checker to test these transistors just below this video. It's a really, really simple thing to do, and you can just buzz through circuits really quick. Basically, it's a go or no-go test for transistors. So this should check like two diodes. So what I'm going to do is, since this is an NPN transistor, the positive lead goes on the base. If it was a PNP transistor, the negative lead would go on the base. So I need to use the positive lead here of my diode checker and put it onto the base. So what I'll do is I'll put this here and I'll just focus in on this here. All right, so now I'm going to check the pin at the top side and watch what we see on the meter here, right? So I'm going to touch the negative lead of my diode checker to the collector here, right? You can see a diode. It's looking good. Now I'll move this down to the emitter, and as you can see, it's another diode. We just verified that this was an NPN transistor. So if I take these leads and reverse them, say I was looking for a PNP transistor, so I'll put the negative lead on the base here. Look what happens. Nothing. Right? Go up here. Nothing. You see, so very easy to verify whether this is a PNP or an NPN transistor. I'll just move the focus back to the board. So that's what we're going to do. So we now know that we have an NPN transistor here, and we would do that all the way along. So if we didn't know this was an NPN transistor, again, I would take this and put this on the base, go here. You can see we have a what looks to be like a diode, I should say, there, and on the top, again, the same. And we would go along and check that. And then this way we can verify that we're dealing with all NPN transistors. So at this point, we know that these two are NPN transistors, and again, we would redo that check here and we would realize that we have 3 NPN transistors. So now that we know that we have NPN transistors in here, we know that the signal is being fed into the base. I'll just zoom on in here a little bit again. Get this out of the way. So we now know that the signal is going to be fed into the base. We can see that we have 2 resistors here, so that would be the biasing, right? If you look at the schematic, you'll see a resistor that runs up here, just above a resistor to the collector, and you'll see that a resistor running down here to the negative. This is what's setting the bias for this transistor to get it right to that point to where it's going to be useful in an audio circuit. You can look at setting the bias on a transistor or setting the bias on a tube like a high stall converter in a car. If you're ready to race, you want to rev the engine up to that point to where it's, say you have a 4,000 stall converter in your car and you're ready to race, you want to rev your engine up right into that point to where your car is basically torquing over and it's ready to go, and then as soon as, the tree comes down, it's, you're on your throttle, right? It's the same thing. You're bringing it up to that point to where it's just at the point to where it's ready to go. And it's the same thing with this. Or if you wanted to look at it like a light switch, you have a light switch that's either off like this. So say it's off, and then it goes all the way up here to become on, right? So you'd know that if you move the switch like this, it's still off, 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 and then all of a sudden it goes click and it turns on. So you would want this just before that point to where it goes click. So that's basically what bias is you're getting rid of all this area in the bottom. And that's what these resistors do. It's basically just getting ready to turn that transistor on. So I have a video here on Patreon as well on basically setting the bias on transistors and bring the transistor to that perfect point. So if you look through the list of videos, you'll find that here as well. So since we know that we have a signal running into the base of this transistor, we're going to have an amplified signal on the collector, because we can see here that we have a single resistor on the emitter to ground, and we have a capacitor running to ground. So obviously the signal path is going to be running out here, right? So what we're going to do is we're going to probe this point here with the scope. Now I'll have my scope on extended sensitivity. Again, basically it's just looking for amplitude. It's, a gibberish measurement. And then we're going to measure this point here, and this is where we're going to actually see some form of gain that we can measure. Now again, you can cheat. You can actually use the circuit within the amplifier itself to see if it's amplifying just by probing this. So basically what we're doing, say you had a vacuum tube oscilloscope or just an analog oscilloscope of any type, whether it's solid state or vacuum tube, and you couldn't get a measurement at this point, you can very easily verify that by going to this point here, and you're going to see some amplitude, because that would tell you right there that that amplifier is working, right? Now, it's always a good thing to do. This amplifier here is a bit of an exception because this thing is so incredibly sensitive, and this is why this is a really good thing to start with, because I can fill you in on some of the tricks on doing this. One of the things that's very good to do is when you put the signal into standard amplifier, say you're working on an audio amplifier, you have an audio amp on your bench, again, from a home stereo system or something like that, and you have your signal generator fed into the input. Put your oscilloscope on AC coupling. So you want the input of your scope AC coupled, not DC, because if you encounter any DC voltage here, it's going to lift that signal possibly off the screen and make things confusing. So for troubleshooting, if you're not looking for a DC level, AC coupling is always very, very important. So AC couple your scope. You'll find that in the menu, and sometimes it's just a switch on the outside. So if your scope has the ability to do 50 ohms or 1 mega ohm, of course you're going to want your input on 1 mega ohm, right? Now, if you're looking for an extremely low level signal, you'll find some oscilloscope probes out there that are ×1 and ×10. ×1 would be the preferred setting for a very, very low level signal. If you're ever using a ×1 probe, be very careful with the input of your oscilloscope. You don't want to basically hit any high voltage DC or anything on that ×1 probe. All right, for this particular application, I'm going to be using my probe on ×1 in the beginning here, just because this is such a low level signal. So having a ×1 and a ×10 probe is very beneficial for troubleshooting. So again, AC coupled times 1, and what I'm going to be doing is probing this point here. Another really good way to know that you're going to find some form of signal is take your oscilloscope and first probe the input to where your signal generator is and get some form of reading on your oscilloscope, so you know that when you touch your oscilloscope to the input, so you know that your signal generator is actually putting something out, is get some form of a visible signal on your oscilloscope. So you want to touch your probe here and you're going to see a sine wave on your oscilloscope, and then when you remove it, it goes away. So now you know that you have a set amplitude on your oscilloscope. When you come to this point here, that amplitude should go high. That's all you need to know if this is amplifying. Really, it's that simple. You can use any type of a vacuum tube oscilloscope, even without digital display, to troubleshoot. It really is quite simple. You don't need to be doing math. You don't need to be working out amplitude. When you're troubleshooting a circuit, when a transistor fails or something goes wrong within that circuit, it's usually yes or no, on or off, dead or alive. It very, very rarely, unless you're looking for an intermittent problem, and that's a completely different type of troubleshooting, and we're going to go through intermittent troubleshooting as well. Intermittents are some of the absolute worst things to find, because if it's intermittent and you're testing it and the signal is there, there's nothing to troubleshoot. So you have to make the thing fail. So we'll get into that here in the future. So there's a lot of instruction here already. So again, times 1, AC coupled oscilloscope, and what you want to do, in this case, I'm going to look for a signal here. I'll give you an example. If you're using an audio amplifier and you're going to be testing an audio amp, you'll have plenty of signal from your signal generator to look at on a normal oscilloscope. And you want to verify that you're seeing something right at the signal generator. Because if you can't see anything here, what's to say if you're troubleshooting, you're going to see anything there? Maybe your scope's not set right, maybe there's something wrong. So you want to be able to see amplitude at this point so that when you're troubleshooting through the rest of the circuitry here, that amplitude is visible. And then as you move along, you're going to be adjusting the scale on your oscilloscope. Basically, you're going to be adjusting the vertical sensitivity as you go along, because the signal is going to start to get really big when we get over to this portion of the amplifier, right? Because it's getting amplified up to a very large state here. So what I'm going to do now is I'm going to put the camera onto the oscilloscope itself, and we're going to start using that picture, and I'm going to show you as we're going along how to put your probe into the circuit and basically how to troubleshoot or follow the signal path right up to this point right here. We're ready to start following the signal path through this circuit, and the first place that we're going to look is the same place that we looked with the spectrum analyzer. So I'm going to put my probe at this point right here. After this, we'll go to the base and we'll look at this right over here. Alright, so the probe is now going to point number 1 here. So now this is open right now. My probe is just open. I had it grounded out. This is with the tip grounded out, so this is just picking up random noise right now. So what I'm going to do is put this right here, and as you can see, I have a little bit of signal. Now if you look down here, you'll see that I'm at about 1 millivolt per division. That's the sensitivity. And there isn't enough here. This is usually as low as most scopes go. So what I'm going to do is I'm just going to click on the vertical zoom, and I can see the signal in there. And as you can see, really, it's just a bunch of noise and gibberish. But I know it's the signal because I'm going to use my signal generator as the reference. So what I'll do is I'll just turn the amplitude down on the signal generator and watch what happens to the signal. See, it goes away. So I know that I am looking at some signal. So I'll turn this up just until I get that last LED lit again. There's about comfortable. So I know that that is the amplitude. There's just a lot of noise mixed with it. So now what we want to do is we want to make sure that that signal is getting to the base of the transistor. So we're going to go to test point number 2 on that sheet that I just mentioned. So this is test point number 2, and as you can see, the signal is still there. Now, we know the signal is getting to this point. This is a good sign. So now, if I go to the collector of that transistor, so I'll just put my probe down here and refer back to the sheet again. So if we go to the collector, which will be this right here, test point number 3, we should see quite a bit of amplitude there. So from the base, which is number 2, to the collector, which is number 3, we're going to see a huge difference because the transistor, if it's working correctly, is going to be amplifying. So again, this is just an open probe, and what I'm going to do is just shut that vertical zoom off. I'll just go over here, shut that off. So now what I'm going to do is go to the collector, test point number 3, and as you can see, with no zoom, I have amplification there. So this is the collector, test point number 3, and I'll go back to test point number 2, and as you can see, there's almost nothing at 2, so you can see we have amplification. That's really how simple it is to verify that that stage is working. When you're troubleshooting, that's all you're looking for is just a rise in amplitude. So I'll go here again, and as you can see on the collector, test point number 3, we have amplitude. Just that simple. So we verified one transistor is working already. Now there is a chance to overdrive this stage or give it a little bit more amplitude than absolutely needed. So I can turn my signal generator up. Now you don't want to overdrive the stage too hard, but you can see that I'm now turning my signal gen up and it doesn't really look like it's overdriving all that bad. Now if we go back to the input here, we might actually be able to see that. See, we can see just barely see that level of signal on the input. So, and that's just basically by turning the signal generator up. Now, of course, the bars on this thing are absolutely pinned out at this point, right? Because we're way beyond where this, you know, what it takes to basically bring those bars right to the top, right? It's way beyond that in amplitude. So you can see we see a little bit there. And if we go back to the collector, we see a whole lot there. Just that simple. It's just that easy to verify that a stage is amplifying from the base to the collector. And again, you want this AC coupled. So now, what we want to do is we want to follow that path. I'll just put my scope probe back on the bench here. So now what we want to do is follow that path. So we're at this point here. So we want to see if the signal is getting through the capacitor, through this resistor, and to the base of the next transistor so it can get amplified again. That amplified signal will be at number 5. So we're going to probe number 4 and number 5 now. So I'll stick my probe at number 4, and we should get pretty much the same thing that we see up here, maybe with a little less amplitude. So I'll go to number 3 again, just so we can refresh what we just saw. Here's number 3. So now we'll go to number 4. And as you can see, it's just a little bit less amplitude because it is going through that 10K resistor, right? This is to stop oscillations. Or to stop the thing from running away, really. Now, if we go to the collector, we're going to see a lot of amplitude if this is amplifying. So we're going to go to number 5 on that sheet. So here we go to the collector, number 5. If I can get it on number 5, there we go. Look at the amplitude there. So I have to turn my scale down. Look at that. We have to reduce it to 50 millivolts now because there's so much amplitude. So from here, right, so that's the collector. That's number 5. So I'm going to go back to number 4, the base again. And as you can see, there's virtually almost nothing there. Whereas if we go to the collector, we can see that amplitude again. So now, if we go over to the next stage, I'll just put this back on the bench. So we've now verified that there is signal right here. Again, we want to go through this and down to here and just repeat again. So we'll have a little bit less signal here than we did here, right? Because we're going through a 10K resistor here. Again, that's to stop oscillations that we don't want. So, and then we're going to go from 6 to 7. So again, from base to collector, and we should see amplification at this point. And then this just goes through the capacitor and runs out to part number 8. We'll trace it right up to number 8 to make sure that we have signal all the way to number 8. So now I'm going to go to test point 6, and then we're going to move to test point 7. So test point 6 is right here. So you can see there's just a little bit less amplitude there. So if I go back to the other side of that 10K resistor, which is basically the collector of this, you can see collector, we have quite a bit of amplitude there, and we have a little bit of drop, again because of that 10K resistor. That's the other side of the 10K resistor. So that's the top side of that 10K resistor, and this is the other side. So you can see it's just reducing the signal a little bit. So when I say the top side and the other side of the 10K resistor, I'm talking about this right here. So I'm going on either side of this resistor. So you can see the drop across that resistor, that 10K ohm resistor. So I'll do that one more time. The top side, so this is basically connected to that capacitor, that's to the collector, and then to the bottom side of that 10K resistor, and you can see the amplitude drop. So that connects to the base of this transistor here, which is test point number 6. So now we're going to go to test point number 7, and again, if this stage is working, we're going to see the amplitude raise up. And now you can see why you wouldn't even need an oscilloscope with any kind of even a graticule for this. Look at how much gain there is there. Let's move this out of the way. I have to turn this way down. So you can see lots of gain there, and that's at 2 volts per division. So you can see like we're actually overdriving it just a little bit. So I can turn this down, and you can see the sine wave cleans up with a bit of noise there, right? So again, any older type of oscilloscope, even that old Heathkit scope that I did the restoration on, would be just absolutely fine for this. Now again, without that amplifier that we're going to design here quite shortly, you can pretty much start off at number 3 right here. So you're using the first transistor to amplify that small signal. Now if you overdrive the input of this, we can still tell that this is amplifying. That's one way of doing this, is we can really overdrive this and see if we can spot the amplitude difference between 2 and 3. If there is an amplitude difference, so if the amplitude is bigger on 3, it really is that simple. We know the thing's amplifying. And then, you know, on to the next stage. So if we had a dead amplifier or something like that, we would know this stage is working. And the same thing is for vacuum tubes as well. Grid to plate, grid to plate, grid to plate, right? So this would be grid and plate on a vacuum tube, right? So we'll go to number 8 here, and this is where our signal ends off. So we'll try number 8 here. So here we go, number 8. And as you can see, the signal is there. And since we have no 10K resistor between the output of that capacitor on the last stage to this point, the amplitude should still be the same as it was earlier on the collector of that last transistor. Again, that collector being number 7. So we'll go number 7. And number 8. So if we came to number 8 and we saw the signal missing, we would know that there's something wrong between that, either the capacitor or there's a broken trace somewhere. And that's really common in power supplies and even audio amplifiers, again, that have leaky capacitors that go underneath the electrolytic caps. So power supplies, this is really prevalent because power supplies really work the capacitors hard. So especially switch mode power supplies, I should be saying. So what happens is they leak out of the bottom seal, and any traces that go below or underneath the capacitor, they rot open, and you can't see them because they're sitting underneath the capacitor. So in this case, you can kind of see the same thing. If you look at the schematic, if that last capacitor was an electrolytic capacitor, so just say this was an electrolytic capacitor, and you can see how that trace goes directly underneath that cap. A lot of the times flaws hide directly underneath electrolytic capacitors because right where the leads come out of the seal on the bottom, and even surface mount electrolytic caps, they leak. They put a little puddle underneath, and that over time will just rot right through the trace, and you get an open connection from this side to this side, and they hide. And this is why it's so incredibly important to test everything right to the end, right? So at this point, we're at number 8, and we still have a signal. So next, what we're going to do is look at the effects of all these other different components just until we get up to this display right here. Now that we've verified that the amplifier portion of this circuit board is working okay, we want to press on. So we ended off at test point number 8 here with the oscilloscope. We see a bunch of wires running off board, and we also see a component here that has a trace that just runs off here to another purple lead that runs off to a switch. So in one position, if we follow these wires, we'll see that it connects this end of the component to ground. And in the other position, it opens this connection here, and it just really just floats at that point. So we want to verify what this thing is. Well, first of all, just through recognition, whenever you see a small rectangular black block on a board like this that only has 2 leads on it, it's a really good chance that it's a diode. Now, if it is a diode, we don't know what type of diode this is. So we want to verify that it's either a, say it could be, because we don't know what the circuit is and what's going on. Is it a Zener diode? Is it a Schottky diode? Is it a standard diode? We really want to find out what this thing is. We also want to find out what way this is installed into circuit. So that's what we're going to do now with a simple diode test. So with the power removed from the board, so the power is not applied to the board at this point, what we're going to do is take a standard diode checker, put this up here like so, and what I'm going to do is I'm going to take the positive lead of my diode checker and put it to test point number 8, and I'm going to take the negative lead of my diode checker and touch the back side of that diode. And as you can see, nothing's happening. So we're going to reverse the leads now. The negative lead of the diode checker now goes to number 8 here, and the positive lead goes to the back side. So now we know that the line side of the diode, the cathode side, is face up. So the line side of the diode attaches directly to test point number 8, and we also know, because of the low forward here, 0.394, we know that this is a Schottky diode. So right there, this is telling us that it is not a standard diode, because a standard diode has usually about 0.6 to 0.7 of a volt forward, okay? And that would also tell us right there that this is not a Zener diode. So we verified a whole bunch of things just with a standard diode test and with some recognition. So I'll get this off the bench now. So now we know that we have a diode here that can be switched in and out of circuit, and the back side of the diode is connected to ground or open, just depending on the switch position. You can check the schematic for this as well if this makes things a little bit easier for you. So we know our signal ends up here, so we know that this is going to go to ground and this is just ground, so the only place that the signal can come out at this point is either at 9 or 10. Now, if we follow these leads, we're going to find through the switch that we can either switch this to position 9 here to test point 9 or to test point 10. So we can route the signal to either this point or to this point. And in one of the positions, this diode is connected, and in another position, this is open. If we do a little bit of further research and very carefully trace those wires on the schematic, we'll find that in the gain position, which means that the signal is going to be coming out at number 10 here, this diode is open. So this is open here. In the intensify position, this is connected to ground, and the signal comes in at number 9 here and goes through this capacitor, and the signal would end up going through the circuit and into this component right here. So since when we click that switch into one position and it attaches this end of the diode to ground, we have a sine wave here and we have a diode with the line end up. What's going to happen? Well, if we attach this to ground, it's going to clip the bottom portion of that sine off because the line end is here. So we have a path for the negative portion right to ground, and then the diode is going to be off on the positive portion. So if it's doing that, what are we going to see on the oscilloscope? Now here's something that might catch you. This is something to keep in mind. Okay, so I'm going to attach the positive of this back up again. Okay. Now what I'm going to do here is I'm going to turn the gain potentiometer right down for this test. So because we're at this point, the gain potentiometer here will cause a little bit of, not much of a movement. It'll just make what I'm going to display a little bit clearer here. So I'm going to attach my oscilloscope probe back up to test point number 8 again. Okay, so this is what we get. Pretty much like what we had before, right? I've moved the gain around just a little bit since then. Not a big deal. We can see that we have this here. Now I'm going to flick the switch here. Okay, so look what happens when I flick the switch. not a whole lot happens. You see that we have a little bit of clipping here, but everything looks, it looks like we lost a bit of gain and, a little bit of clipping here, but not a whole lot is happening. Why is that? Well, we have a diode. I'll just remove the probe lead here again. We have a diode that's going to be switched in and out of circuit here, this diode. If this is going to clip the negative portion of that signal off, what are we going to have? We're only going to have the positive portion of the signal there. In order to see just the positive portion of the signal, what do we need to do? Well, we need to change the coupling on our oscilloscope to DC in order to see that. So when we're troubleshooting an unknown signal, we want to have our scope on AC coupling. When we have a diode here effectively creating a form of rectification, because we're going to have this being rectified, or we're going to have basically just a positive pulse here, the bottom portion again being clipped off because of this diode, we want to be able to see that. In order to verify that, we need to use the DC coupling on our oscilloscope. So what I'm going to do is DC couple the scope. We'll go into the vertical menu and it says coupling here. So right now AC is selected. I want to select DC. Click close here. Now, what I'll do is I'll flick the switch back to the original position here. Okay, so again, you can see, because at this point here we have an AC signal, right? This looks normal. Now watch what happens when I flick that switch. We can see the difference. Whereas before, if I go back to AC coupling, you can see how that could get very confusing, right? Because now if I move the switch back and forth, there's not a whole lot of difference. Where we see what we want to see is when this is coupled to DC, because we have a diode there. Again, basically creating a form of rectification. So we're clipping off the bottom portion of the sine wave. Now, we know that since we have this present at this point, I'll just put this down here. Since we have this present at this point here with this, the anode end of the diode connected to ground. So we have the cathode end, which is the line end facing up here. We know that this is going to run through a VR and then a switch and then back out to this point over here. Now, we can very easily verify that by just following the wires to the switch. Again, if you want to follow the schematic at this point, you're welcome to do that. So with this in the gain position, because this thing here would be in some form of a device and it would obviously be labeled at this point, right? So we'd flip it over and we'd find that this is in the gain position that would be marked gain. If we follow the wires, we would find that the gain position comes out here at number 10. Now, in the gain position, this is open. If we click this to the intensify position, it routes the signal to number 9 here, and it closes this diode. So we can verify that the signal is getting to these points here by using our scope. So what I'll do is we'll go back and probe, again, this portion right here. Now what we're going to do is, since we know we're following the wires here, we want to find out if this is getting, because this is now in the intensify position, to the intensified area. That intensified test spot is now number 9. So we go to number 9 and we see nothing is there, but we have to remember to turn the gain control up. So here we go. Gain control maximum. Now, since this is pretty much a straight through connection, if I go back to number 8 again, we should have the same signal. There it is. So now we know that the signal is getting there. So we know that the signal is basically getting through a switch and getting through the potentiometer, and now we can also vary the gain by moving that gain control up. So we verified a whole bunch of things. We verified a switch connection, and we've also verified the potentiometer just by doing this. Now, what we want to do is we want to see if we can put this signal over here. There's that signal. The same signal that we see over here. So now we can see that we have a signal on both 9 and 10, depending on where we put that switch. We can also see, because we have a semiconductor here, and we have a bunch of things in here, we're going to also get a path that's going to run back here, and we're going to see a little bit of signal over here. And again, I'll start talking about why we see bleed through and all that kind of stuff in another episode. Right now, we'll just keep this simple, and we'll just follow the signal path. Now, we see the signal at number 9 here when this is in the intensify position. So what I'll do is I'll click this back to intensify, and we'll go back to number 9 here. Get this back on to number 9. Click this to intensify. So there we go. What happens if we move now to test point 11? What are we going to get back at test point 11 right here? Technically, we're going to get what looks to be like a standard AC signal again. It should be at the center of the screen. So we'll go from 9 to 11. Let's get this piece of paper out of the way. There we go. So again, number 9. And now we're going to go to test point 11. Look at that. Now that is running into our pass transistor, which is right here. Again, we would verify this component the same way we've verified this component. Now, we don't need to go through this all over again, because just use what we used earlier to find out what this component is. You will find out that this component right here is an NPN transistor just like this. We can see that the positive is running right over here to the collector. If we were to ohm out this trace, we would see that this trace just runs under the transistor and over to what looks to be like another diode. This component looks identical to this component, and if you were to look really carefully, you would probably see the same kind of markings on the tops of both of these components here. So that would tell you what's happening here. Now again, we would take our ohm meter and find out which way this diode is situated into circuit, and we'd get a really good idea of what's happening. Again, looking at the schematic, if you want to look at the schematic, you'll find that the cathode end is here. So again, we're getting rectification happening here, and we can see that we have a capacitor and a resistor running off to ground. Our signal goes into 12. Now, the LM3914 needs a DC level in order to make this basically go up to whatever LED we want and then come back down again. This capacitor here that we see is just acting as a filter for that DC level, and we have a bleeder resistor here, which gives us a decay time. Okay, so if we didn't have this here, it would come up and it would slowly drop off. So we want to discharge that capacitor fast so that we can make that level on the LEDs drop again. So what we'll do is we'll now move to number 12 here, and we'll take a look at that DC level with the scope. Now, this component here could get tricky because this isn't designed to turn this directly into nice clean DC. If we wanted to do that, this display would take a long time to go up and a long time to come down again, because we'd need one heck of a resistor here and we'd need a lot of drive. So this is a balance point in the design. Down the road, I'm going to get into telling you how I figure out these balance points. All right, so again, we're just troubleshooting in this episode here, so we'll keep this easy. So what I'm going to do now is go to test point 12, okay? And as you can see, again, we have a DC level with just a little bit of ripple. Now what I'm going to do is vary the amplitude of my signal generator, and you'll see that that DC level will come back down to the line, and it will raise again. And as you can see, as we get to the top, we can get a bit of ripple at the top, but as you can see, we have a DC level that's just basically moving up and down. That DC level is what's moving our bar graph up and down, just that DC voltage right there. And that's what that diode is doing. Now, the introduction of the pass element, that little transistor that you see there, is basically, it takes a bit of drive to turn this transistor on and off. And because it takes 0.6 of a volt to turn this on and off, and it does take a bit of drive, we get a bit of a floor on the bottom. So where we would normally see noise on this display, when we click this into the intensify position, this is going to drop off. The function of this diode on here is just to step up gain, so a bit of pre-rectification for the intensified position, just to get the gains a little bit closer, so we have a little bit more gain in the actual intensified position. That's really just what this diode is doing, pre-rectification, or basically giving us some DC here, some pulsing DC at that point, trimming the bottom portion of the sign-off is what I should be saying. That's really all that's happening in this circuit. So we can see that we can vary the DC level, and that's following the signal all the way to this point right here. And again, we can see that we have a very nice DC level at that point. So effectively, we've gone right from the beginning right to the signal input. Now, if you have any questions or anything else that you would like me to touch on in a future episode with troubleshooting a circuit like this, please feel free to leave this down below in the comments section, and I will revisit this in more depth in the future when we're testing another circuit. If there's something in here that is relevant to another circuit, I will spend more time on that. We will get into pass elements when we start getting into power supplies. I'll explain exactly what pass elements do. Basically, this thing is, as a pass element, this thing is just acting as a variable resistor. That's all that that thing is doing. So a solid state variable resistor really is what a pass element is. So again, feel free to leave that down below. Now what I'm going to do is I'm going to explain the gain calculation for this section here. In order to calculate the gain of this amplifier, it's a really easy process, and you can use this process for other things as well. Say you're designing an amplifier that uses op amps and you want to figure out how much gain there is, use this process for that. If you're designing a vacuum tube audio amplifier and you want to know how much gain your vacuum tube audio amplifier is making, use this process for that. You can even calculate the gain of your home stereo system audio amplifier if you'd like. So we already know that if we feed 27.5 microvolts into this area right here, it will light these LEDs right to the top and comfortably light this last LED. So just comfortably lights that last LED. When I fed this with 27.5 microvolts, I took a reading at this point with my oscilloscope, and I got 1.85 volts out. So these are both RMS readings. So we can do our calculation from that. So the input is 27.5 microvolts. Pardon my scribbles. So that's at test point number 1. Now we need to convert this into volts to do this equation. So 27.5 microvolts turns into 0.0000275 volts. Now at test point number 8 on the sheet here is where I read this with the oscilloscope, and I got 1.85 volts out. And these are both RMS. So now, in order to do this equation, we use this and this. So very simply, we get our calculator right here. And what we do is we take 1.85 divided by 0.0000275, and we get a ratio of 67,272. So 67,272 is our ratio. Now to calculate this into gain is very simple. We go 20 log 67,272 gives us 96.5 dB gain. That's a lot of gain. So we got 96.5 dB gain. And that's how simple it is to do this process. Now again, if we change the transistors in here, or let's get this out of the way. If we change the transistors in here and we look for, a transistor with higher HFE, or something as simple as just upping the value of these capacitors will take the gain of this thing and up it a lot more. So remember how carefully I had to trim these capacitors so this thing would just be on the verge of possible oscillation, but in a safe zone so that we get a nice display. So we're really pinching a lot of gain out of this, and there's still a lot left over. If you were to take another one of these capacitors and put it here, it probably would turn into an oscillator. So lots and lots of gain. 96.5 dB gain. So I hope you enjoyed this troubleshooting episode. If you did enjoy this, you can click the heart symbol below and let me know, or leave a comment below. That's fine as well. Again, in the future, we're going to design a very high gain amplifier to attach to any of our oscilloscopes. If you want to use an old vacuum tube oscilloscope or even a more modern oscilloscope that, say, doesn't have a zoom feature, we can use this and get a nice clean result with a signal, much cleaner than what you saw on this oscilloscope here. That really is just a gibberish, amount of noise and everything in there. And of course, the readings on the side of the screen really didn't mean anything, right? So this should give us a nice clean reading with an amplifier directly tied into this point. We should be able to look at low-level signals like that with ease, and of course do the calculations at that point. So a lot of really neat stuff coming. There'll be a lot more troubleshooting videos. This is just video number 1. I plan on troubleshooting all sorts of different circuitry, power supplies, radio receivers, transmitters, you name it, all sorts of different things. So we're going to be troubleshooting all sorts of other circuits. We're starting off with this one because this had a schematic, and I designed this circuit so I can lead you through this and you can follow along on that schematic. As we go along, schematics will no longer be available, and we're going to have to figure out all of these circuits just by looking at the circuit board and following traces. And before you know it, you're going to be a super troubleshooter. See you next time.